Chemical injectors use the Venturi effect to inject chemicals into the water stream. The Venturi effect works by forcing water through a conical body, which creates a pressure differential between the inlet and outlet ports. The higher the water velocity, the greater the pressure differential will be. This pressure differential creates a vacuum inside the injector body, which is used to draw a second fluid into the primary flow. There are several different brands of injectors used in the car wash industry. All of them work on the same Venturi effect principle. Material of the body construction can vary between brass, stainless steel, and kynar, for example. It is important to choose material that is compatible with the chemical being injected. An O-ring, ball, and a spring can be found inside a chemical injector. These prevent water in the line from backflowing into the chemical injection line. These materials also need to be resistant to the chemical being injected. Chemical injection rates can be controlled through water and chemical screw adjustments, or fixed orifices, known as metering tips. Chemical injectors with adjustment screws can be adjusted to have an infinite number of chemical injection rates. A metering tip has a predetermined orifice size. Depending on the metering tip used, the next largest or smallest tip can vary the chemical injection rate by over 40%. All metering tips are colored to make it easy to identify the orifice size. Dima tips are by far the most popular. They come in standard tip sizes and ultra lean sizes and dictate the water flow rate through that particular injector. Fixed orifice injectors used in the car wash industry vary in water flow rates from 1 gallon per minute to 5 gallon per minute or more. Some injectors are color-coded to indicate the water flow rate, and others have the orifice size printed on them, and some have both. Metering tips should come with a dilution ratio chart. This dilution ratio on the chart should only be used as a guide to show what the tip sizes are in relation to each other. There are too many variables, such as the size of the injector, flow, pressure, and chemical viscosity that can impact dilution ratios. Per the standard size Dima tip chart, the smallest metering tip is tan and the largest is gray. Per the ultra lean tip chart, the smallest tip is copper and the largest is lime. This chart can be very helpful when trying to determine what tip will provide the target usage per wash. For example, if the usage is 30 milliliters per wash with a red tip and the target is 21 milliliters per wash, how do you determine what tip will give you the target amount? Take 30 and divide it by 21. Multiply this by 73, as shown on the chart. The answer is 104. According to the chart, 102 is the closest number to the answer of 104. Therefore, you'd use a light blue tip. Let's say usage is 21 milliliters per wash with a light blue tip, and the target is 30 milliliters per wash. Take 21 and divide it by 30. Multiply this amount by 102, as shown on the chart. The answer is 71. According to the chart, 73 is the closest number to the answer 71. Therefore, you would use a red tip to get the target used of 30 milliliters per wash. This same approach can be used to predict usage per wash if using the next larger or smaller tip. For example, if 20 milliliters per wash is obtained with a pink tip, it will be easy to predict the usage for the next largest or smallest tip. Usage with a light blue tip, one tip larger than the pink, will be approximately 26.5 milliliters per wash. This is calculated by taking 170 and dividing it by 128, and then multiplying by 20. Usage with a turquoise tip, one tip smaller than pink, will be approximately 13 milliliters per wash. This is calculated by taking 170 and dividing it by 256, and then multiplying by 20. This is an effective method no matter what column is used on the Dima chart. If there is a chemical application problem, troubleshooting a chemical injector should be straightforward. If little to no chemical is being applied, the most common cause of failure is from a clogged metering tip. Metering tips can easily clog due to their small orifice size. Remove the tip to inspect for debris. If easy to do, remove the debris, but be careful not to use anything that may change the size of the orifice. In most cases, it is much easier to simply replace the metering tip with a new one. Another cause of little to no chemical being applied is caused from too much back pressure from a clogged foamer pad or housing, too much air pressure, too small of nozzles or openings, outlet line size is too small, the outlet line is too long, or too large of an injector is being used. Too much back pressure can be caused from one or a combination. Even if set correctly, all these will contribute some amount of back pressure. Foamer pads can become clogged for 3 reasons. a buildup of chemical, debris in the water, or the foamer pad has compressed too much. Switch to a different chemical if it causes buildup. Install a 5-micron filter if there is excess debris in the water. Use a different foamer pad material if it frequently compresses too much to allow for adequate water flow. Too much air pressure is an enemy of injectors. As a rule of thumb, the outlet of an injector will be half that of the inlet pressure. If the inlet pressure is 150 psi, outlet pressure will be approximately 75 psi. If the total back pressure in the system exceeds or equals 75 psi, the injector will no longer draw chemical. Reducing the air pressure can easily reduce a portion of the total back pressure in the system. If the nozzle sizes are too small or there aren't enough, for example, some were initially capped or plugged by debris, this can cause excessive back pressure. Remedy by installing higher flow rate nozzles, uncapping nozzles, or removing debris from the existing nozzles. Some wash sites have multiple wash bays. If the pump stand is too far away from the car wash, excessive back pressure can develop. Two possible solutions are to install an injector capable of handling a larger line on the outlet, or install an injector with a lower water flow rate. If water leaks from the metering tip when the tubing is removed, it means the ball and spring are not properly seated or the O-ring has failed. Depending on the brand of injector, repairing might be possible. If not, it will require a new injector. If the injector is being used for a pre-soak and little to no pre-soak is being applied, it is possible the inside of the injector has a hard water buildup. A white chalky substance is a sure sign that the injector is suffering from a hard water buildup. As the buildup increases, the more it will interfere with the Venturi effect. The injector can be cleaned using an acid, such as lime away, or it will need to be replaced. To prevent this from happening in the future, soften the water or switch to a pre-soak such as CleanTouch 360, a hard water compatible pre-soak that can handle up to 20 grains per gallon of water hardness. Air leaks on the suction side of the injector will also cause reduced chemical flow. It is easier to draw in air than it is liquid. Inspect the tubing around the metering tip to make sure it has not become loose from frequent removal or if the tubing is partially on the injector. Replace the tubing or cut off a short piece if the tubing is too loose. If air bubbles are being drawn through the chemical line, check for all sources of possible leaks between the chemical injector and the container. It is possible injectors are drawing too much chemical, even if the correct injector size and tip are being used. If this happens, the likely cause is the metering tip has not been properly installed on the injector. If the metering tip is loose, it is possible for the chemical to flow around it instead of being drawn in through the orifice.